All right, so the last time we were talking about the centripetal force and the universal law of gravitation, and then really putting the two together, and also realizing that when something's traveling in a circle, um, the, uh, the velocity is 2 pi times the distance the object is from the center of the circle. So sometimes I call that radius, divided by the period. And so if you put this in for the velocity for the centripetal acceleration equation, and then put these together again, we're not going to have to do this. Not the mathematical steps to do this, but really this is what's important. Is you remember in the last chapter, in chapter 2, we found Kepler's third law of planetary motion, which said a cubed is equal to p squared. So if you look in this equation, right? So this is actually the modified version, and this is what Newton did. Newton says, "Hey, wait a second. If I, again, he's the one who actually came up with this formula right here. This one had been known at the time, and of course, certainly this is just distance divided by time. So the distance here is it's the distance from the center, right? So that's sometimes also known as the radius, and then so when you put all these together, notice this it has the exact same form, right? Like if I put the p over on the other side and ignore everything else, that's exactly like we discussed in chapter 2, where this is what we called a the semi-major axis cubed is proportional to the period squared. All right, but what this equation now does for us is it actually introduces mass, right? So Kepler, for example, applied that equation, a cubed equals p squared, is only for an object going around the sun, in orbit around the sun. Now, this equation can be used anywhere in the universe when one object is orbiting another object. Right? And so if you know the period, if you can measure the period and you measure the distance between the two objects, you can work out the mass, right? Like what the actual mass is, not in some arbitrary units. This is actually done in kilograms, right? So, the 4 pi squared is just a constant, so it has no units. The distance has to be in meters. Big G has to be 6.67 times 10 to the minus 11th, because that's what it always is. And then the period here has to be in seconds. So even if I'm going to do several examples with this, but then if you have that, right, if you know what D is and you know what P is, you can work out what the mass is. And so you can do this for the sun. You could do this for what the Earth is, the mass of the Earth as the moon goes all the way around the Earth. And in fact, Isaac Newton did that. And this, these discoveries of the mass of the moon and the mass of the sun. Well, he didn't actually work out what the mass of the sun was. Because he didn't know the value of big G. But within 100 years actually less than 100 years after he passed away, we knew what big G was, that 6.67 times 10 to the minus 11th. So once you know that, you can actually work out what the mass is. And so people knew that, after Newton had come along, they realized what a great insight he had into the universe, and it really inspired people in a way that's really difficult to understand today, right? I mean, it just kind of opens up the universe to human exploration using the scientific method, in all sorts of areas, right? I mean, in chemistry and in biology, all these things have humans have been devoted to this stuff and know a lot more about it now than they did 350 years ago, and we're constantly learning more and more about the universe because we use this thing called the scientific method. All right, which, just as a reminder, right, it's really important to understand this, because it's only been around for the modern scientific method has been around for about 400 years. I mean, there was some evidence, like if you go back to the time of the Greeks, right, and you go to, like, for example, Aristophanes, right? Remember, he was the guy that measured the shadow of an obelisk in Alexandria and compared that, if he's the one who figured out the size of the Earth, so he actually made measurements, and used what we would consider, the scientific method, right, to discover the size of the Earth. Uh, what Newton and Galileo had done, and even Kepler as well, is to use the scientific method to really start to understand, the cosmos, to understand the universe, the universe that we live in, and instead of just speculation about do we live in a sun-centered universe, or do we live in an Earth-centered universe? That's pretty much the kind of thing that they thought about in the Middle Ages and stuff. But this brings science into a mathematical foundation. All right, so we're gonna look a little bit more into that right now. This is what's called the surface gravity. All right, so we experience a surface gravity, an acceleration due to the mass of the Earth and the size of the Earth, of 9.8 meters per second per second. Right, that's our surface gravity. But different worlds have different surface gravities. I think I mentioned this before, that on the surface of the moon, things would weigh, and so the surface gravity dictates what the weight of things will be. So on the moon, for example, it's about 1/6 that of the Earth. On Mars, it's about 1/4. All right, so and of course, remember, gravity is why things are round in astronomy, right? I mean, there's a reason most things are round. Not like, for example, the asteroids, right? There's many asteroids that are definitely not round, and the reason for that is they're not large enough to self-gravitate into a sphere, right? Most things are spherical in astronomy that we come across, with the exception of things like asteroids, right? Because they're just not big enough there actually are some that are a bit larger and they are round, but a lot of most of the asteroids that live that exist between Mars and Jupiter are they're kind of like potato shaped looking things, that they're not perfectly round, like planets or anything like that. All right, so here, so this equation right here. This is what we want to know. This is, so if you plugged in the numbers for, and I'll do an example of this. If you plugged in the numbers, of course, remember, big G is always the same value of 6.67 times 10 to the minus 11th. M is the mass of the Earth, right, which we know that value quite well, and R is the radius of the Earth. If you plug those numbers in, right, the mass of the Earth in kilograms and the radius of the Earth in meters, and of course, big G is what it always is. The acceleration, the surface gravity of Earth is 9.8 meters per second squared. So there's the one for the moon. The moon is about 1/6. I mean, it's almost a 6. Anyhow, all right. like Jupiter is much more massive than the Earth, and so things would weigh a lot more, 3 times more on Jupiter. That's kind of a miss. I don't like this one right here for Jupiter. Let me explain, because Jupiter doesn't actually have a surface. It's not like it's not like the moon or the Earth or any of the rocky planets. It's a gas giant, and so you can't really stand on the moon on Jupiter. All right. So anyhow, um, that's not a really good. I mean, you can do the comparison, obviously, because the mass of Jupiter, the radius of Jupiter, but there's no surface to stand on. All right. So anyhow, and then we come to the final equation and I'll mention the orbital velocity. So this is the one that I'm about to show you is the escape velocity. So this is the velocity it takes to leave an object and never come back. All right. So that's the escape velocity, which I mentioned, of course, at the beginning. All right, so let's see. What is this about? This is small mass, which is our moon, equal lower than escape velocity. So, yeah. All right. So showing you. So this is really what I wanted to show you. All right. So this is the escape velocity equation. If you take away the two, so you just don't include the two. Right. If you did the same equation, but where it's the square root of big G times m divided by r, where m is the mass of the object and r the mass of the planet. You're usually talking about a planet or a large moon or something like that. And r is the size of it, the radius of it, right? So like the circle, if it's a circle, it's always a circle. It's a sphere, and r is the radius of the sphere. If you take away the two, this equation, the v escape becomes the orbital velocity. So the orbital velocity is slightly less. Right. So when you do this for the Earth, it's about 11. It's actually closer to 12,000 meters per second. So when you do this, the calculation, big G is what it always is, 6.67 times 10 to the minus 11th. M is in kilograms, R is in meters. Then the answer, the velocity comes out in meters per second. Often what we'll do, though, is we'll convert that to kilometers per second, because a lot of escape velocities are in kilometers per second. So notice, there's escape velocity from the moon, there's the escape velocity from the Earth. So this velocity, it's like 11.5. It's actually, they're not shown. I'll do an example to show you exactly what it is. So you'll be able to do that. Or you'll see an example of it. But the thing is, like, if you were to convert this into, a lot of us don't think in kilometers per second. If you raised in the United States, then of course you think in miles per hour, right? And so this value is actually closer to, in miles per hour, about 25,000 miles per hour, right? So that's the escape velocity from Earth. That's why you need a rocket to be going there, to be traveling that fast. Which is why, we started building rockets, we just started about 100 years ago. Nothing that could escape the Earth. Just to mention, so if you take the square root of 2 out of this and you just use these values, instead of 25,000 miles per hour, you get about 18,000 miles per hour. And that's the orbital speed. Like, that's how fast the International Space Station is traveling, or, any of the satellites that are going around the Earth. They're traveling at the orbital velocity, which, you just take this square root out square root of 2 out, and that's what the value